Good morning, everybody. And with internet down, I figured I might as well try to throw something together for you. This way we don't lose any time. And you can keep up with the material. Please don't hate me for this, but it's kind of my job. I got to do this. So what I wanted to do first was to just go over some of the homework problems and then introduce as quickly as I can something called a conical pendulum, which you may all recognize because if you've ever been on the swing ride at Bowcraft back in the day when you sat in a swing and went around in a circle, that's a conical pendulum. But first, I would like to go over some of this homework. If you feel that you got this homework, you can obviously fast forward through this video to get to the next section, which is the conical pendulum. But this is a horizontal circle with friction. So we draw our horizontal circle. And we always draw the free body diagram either on the right or the left. So I'm going to draw it here. Normal force, gravity, and always the friction toward the center. After that, please don't memorize anything. There is nothing to memorize. You sum the forces that cause the mass to move in a circle. Sorry, that should say squared. And we sum the forces in the y that cause the mass to accelerate in the y. Now this car is not accelerating vertically. Here, for the forces that cause circular motion, we have mu times the normal. That's it. It's just friction towards the center, causing the mass to move in a circle. In the y-axis, this one's a little bit different. Just be aware of that. There's a normal force up, but then there's this creates a 200 Newton force up. All right, well, I guess we should add that to our free body diagram. There's an additional 200 newtons up. No big deal. We just add that to our free body diagram and therefore add it in our y-axis. So we have plus 200 newtons minus the force of gravity, which would be 70 kilograms because the mass of the person and the bike together times 9.8 meters per second squared equals 0. Solving for the normal force, we get 70 times 9.8 minus 200, we get 486 newtons. So this is like one of those cases where actually the mass is not going to divide out. After this, though, we can substitute our normal force in. We have mu times 486 newtons, causing the total mass, 70 kilograms, to move in a circle of radius 15 meters at 8 meters per second. Sorry, I'm reading the problem. 8 meters per second squared, all over our radius of 15 meters. Solving for this, you would get that mu equals 0.615. And that's it. But some people in the past have just didn't know what to do with that 200 newtons, or they made the 200 newtons the actual normal force, but they are completely separate forces. Some people memorize that you can cross out the mass or divide out the mass, but that's not always the case, which is why I want to bring this one up. All right, the next problem that some people get stuck on, which is why I'm addressing it, is number 5. And this is hangs freely in the seat. That means there is no normal force. Your free body diagram is at the top of the circle and it's just the force of gravity. This is that weightless problem. So we sum the forces that cause the mass to move in a circle. We have gravity positive because it's towards center, causing the mass to move in a circle. And I guess we're solving for R. Well, R is simply v squared, 120 meters per second squared, all over g, which is 9.8 meters per second squared, and we get basically that it's around 1,470 meters. So there's that key phrase, hangs freely, does not push against the seat, or even the term weightless. And the last problem I'd like to do is number 4, which is a vertical circle where there's something being swung in a vertical circle on a rope. And remember that we focus only on the top and the bottom of our circular path when drawing the free body diagrams. For this one, The good thing is that gravity is always down. You don't have to worry about that. Tension is always toward the center. So we have the force of the rope toward center. Tension is always toward center. If you ever swung something on a rope and your hand is in the center, you are always pulling towards the center of that circle. Remember that toward center is positive. I'm actually going to take a second to say, hey, these are all positive. That's negative, the gravity at the bottom there. Afterward, we're going to do the sum of the forces for each top and bottom. But there is this thing about 79.58 RPM. So how do we deal with that? Because that's not the period. All right, this 79.58 RPM. That's 79.58 revolutions per minute. So if it's okay with you, I'm going to write per 60 seconds. All right, you can flip that and actually write it as 60 seconds for every 79.58 revolutions. If you do 60 divided by 79.58, you find out that the period is 0.75 seconds. Seconds is the unit for t, period. We now know the radius and the period. Actually, the first thing I'm going to do is solve for the velocity, which is 2 pi r over t, or 2 pi times our radius, which is 0.6 meters. That's the length of our string. And the period is 0.75 seconds. And we get that you'll have to forgive me because I'm doing this right now. The velocity is 6.32 meters per second. All right. Now that we know that, and I'm doing this one because usually this is where people have trouble. It's on the RPM issue. After that, though, just draw a free body diagram. Oh, we did that already. Sorry. Just use your free body diagram to set up equations. We have the sum of the forces that cause the mass to move in a circle with velocity and radius r. For the one on the top, we have Ft positive, mg positive equals mv squared over r, or we're solving for the tension. That's Ft plus the mass, sorry about that, is 1.3 kilograms times 9.8 meters per second squared equals mass, 1.3 kilograms, velocity squared, all over r, which was, 0.6 meters, and we will find out that the tension at the top is equal to, hopefully, whatever that answer says, 41.4 newtons. If we do the free body diagram at the bottom, when we sum the forces that cause the mass to move in a circle, I'm looking at the free body diagram, I'm not memorizing a thing. I drew my FBD, and then I'm like, oh, look, tension's positive, gravity is negative, equals mv squared over r. I will sub in some numbers here. We have tension minus 1.3 kilograms times 9.8 meters per second squared equals that mass. It's funny, as I'm writing this, my watch is blowing up because the teachers are all panicking. Not really panicking, but slightly panicked, slightly, what are we going to do about today? Hopefully this is okay. And we get that the tension is whatever the answer is. About 66.9 newtons. So those are the problems I wanted to go over. And if internet is restored today, then, there'll be office hours in the afternoon if you want to stop by and ask for some help. But this is just going over the homework. What we have to do now is introduce conical pendulums. Conical pendulums. Fancy name. Again, it's if you've ever been on a swing ride where you sit in a swing and it's attached to a long chain and it goes around in a circle. The swing ride at Bowcraft, if you've been to Great Adventure, they have this swing ride, and it kind of looks like this. There's you on this swing ride as you go around and around in a horizontal circle. Okay, that's basically the whole scenario. We can draw a free body diagram for this. It's friendly. Gravity, always, don't forget about gravity. And then the only other thing acting on you is the force of the rope or the string or the chain or whatever it is. There's this Ft at an angle theta. Okay, so the rope is at an angle, but we are moving in a horizontal circle. So don't panic about this. We have a free body diagram. Let's fall back on our skills. Our skills are to set up math based on a free body diagram. I'm going to do that right here. I'm going to, actually I'll do it a little bit below here. We're going to sum the forces that are causing the mass to move in a circle with a velocity of v and radius r. And we're going to sum the forces in the y that cause the mass to accelerate in the y. Again, there is no, the y, this comes up a lot. It's MAY because there is no vertical circular motion here. So it's just regular old AY, which by the way, for this problem is 0. The math that follows, just looking at the free body diagram, you have the tension force towards center at an angle, and hey, this is like x-axis stuff, so it's cosine theta equals mv squared over r. In the y-axis, we have a tension force sine theta minus the force of gravity equals 0. I'm just going to move that over so you can see something. All right, so right now we have two equations with two unknowns. This will not be the first time you've seen something like this. This should remind you of static equilibrium, where in the x we had cosine and in the y we had sine. Often, but not always, you will most likely have to isolate an Ft, sometimes, not always, isolate Ft and sub into the other equation. Okay, may I suggest isolating the one with the cosine? All right, this way, when you sub the cosine, whatever that is, into this one here, you will end up with your friend sine over cosine, which you know to be tangent. Now, that's not always the case. It depends on what you're given in the problem. You may have enough information that you can instantly solve numerically for the tension force. But if you don't know the tension or the angle, it's not going to work. You're going to have to do substitution. All right, and that's a conical pendulum, and this is exactly what I showed my people last year. There's no sample problem to do because the free body diagram is always the same. It's tension at an angle and gravity pointing down because it's the swing ride at Beaucraft. One thing I do want to bring to your attention though is sometimes a problem will tell you the length of the string or length of the chain or whatever. However, that is not the radius of our circle. That's the length of the chain. Therefore, hopefully you see this, these two are related by cosine, so the radius is just the length times the cosine of the angle, okay? It's just a right triangle. We have a hypotenuse and we're looking for the x. And that basically sums up everything we are doing. Sorry, I was looking for the homework assignment, but I have no mouse. Oh, that's just fabulous. I like that. The homework assignment, sorry to do this to you and take this long, is called what, people? Do you know what it's called? It's already on Classroom. You know what it's called. It is called Horizontal, Vertical, and Conical Pendulums. So this is a review of everything we've done. I mean, but this one is a car going in a circle. There is an additional downward force for this one. Here you're upside down on a vertical loop and a roller coaster. This one here, we are looking for the angle of a conical pendulum, 3 and 4 conical pendulums. And this is the one where you definitely have to do sine and cosine. And then number 4, again, is a conical pendulum. Basically, if it asks for angle or it gives you an angle and it's a horizontal circle, we're talking conical pendulums. So that's for tomorrow's class. I hope that we get internet back up and running. Otherwise, people, please do your best with this. I'll be available for office hours once the internet is back up. And I guess that's it. Please email me, stop in for office hours if you have any questions. All right. Take care, everybody.